Deep learning with Python. Hello everyone, my name is Dimitris, as Susanna talked to you about before, and we will go together through the study sessions. So let's see some details about the study sessions. The idea is to go through the chapters of the book, Deep Learning with Python, second edition, by François Chollet. So here you can see the book. And we will go through the code, the notebooks that already exist, and it's very good that they are open source. And so for each chapter, you can find the code that we will read and run under this link. So in GitHub, Chollet, Deep Learning with Python notebooks, and it looks like this. So here you can see all the notebooks with all the code that we are going to read and explain and run. So the duration of each session will be more or less 1 hour, depending on the content. So some might be a bit smaller, some a bit bigger. And the questions, how many questions there will be. Regarding the questions, as Susanna already said, it's good to feel free to ask questions at the session, the Zoom chat. And my colleagues, Susanna, Anugra, and some others will try to facilitate this. So if needed, the questions will be answered during the presentation. For example, if there is some misunderstanding about the code that we are running or do something strange. Otherwise, we will hold a Q&A part after the main presentation where you can ask the questions and we will try to explain things. Now, before we start the chapter, 3 recommendations, as you can see here. First of all, we strongly recommend that you read the chapter before the session. So it's good because you will first of all have an idea of what we are going to talk about. You will have crystallized questions, things that you don't understand and you want to understand better. Also, if possible, try to read and run the code before the session. As I told you before, the code that we are going to run is more or less the same as the notebooks that are available on GitHub. And because all the code will be in Python, in case it's needed, I suggest that you refresh your Python skills because everything will be Python. So apart from that, let's start with chapter 1. What is deep learning? So this is the title of the first chapter. Let's see the contents. We will see 3 things in this chapter. First of all, the high-level definitions and fundamental concepts of what is AI, what is machine learning, what is deep learning. We will go through a short historical timeline of the development of machine learning and AI. And we will close with some key factors behind the deep learning's rising popularity and the future potential. So let's continue. Now, the thing is that there is too much hype and noise around AI. So it's good to try to distinguish among what is noise and what is actually something that is doable or achievable. We are promised of a future of chatbots and self-driving cars and virtual assistants and everything. But as I said, it's important to recognize what is signal and what is noise. So this is important because probably AI will play a very important role in the next years. And as it's mentioned in the book, our future is at stake because it will probably change dramatically many aspects of our lives. And the important thing is that we have an active role. So people that not only are here, but people that deal with deep learning, with other AI techniques, they will be the ones that will shape this future. So we have an active role to play, and it's important to understand what it is, how it works, and what we can do, what we shouldn't do, etc. So let's start with the definitions. Artificial intelligence. We will start with this. So AI, when it was born, although there were many things related to AI and concepts and more or less theoretical or philosophical, as a field of research, it started in the 1950s. So specifically, we consider that artificial intelligence as a field of research was crystallized in 1956. So in 1956, there was this workshop, this summer workshop organized by John McCarthy, among others. And it was the first workshop, the first attempt to make a concrete research on this field. It was not a field before. And there is a proposal, it's mentioned in the book, and I thought it's interesting to actually see the proposal, not all of it, it's some 17 pages, but just to read a few parts. So this is the proposal from 1955, 1 year before this summer research project that was held in 1956. I hope you can read from my screen. It was initiated from John McCarthy, Minsky, Rochester, and Shannon, Claude Shannon. So big names. I mean, Claude Shannon is considered the father of the information theory. John McCarthy is one of the founders of artificial intelligence. So here is the proposal. We propose that a 2-month, 10-month study of artificial intelligence can be carried out during the summer of 1956 at Dartmouth in Hanover. And here is the main idea. So the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So this sentence here is actually the core of what they expected artificial intelligence to be. We can notice that, for example, they mention simulate. So the initial idea for machine learning is to simulate some specific behaviors, like, for example, the learning or other features of intelligence. So what would be, we will see later on what will be the scope. And another important detail here is that they would try to precisely describe this. So they don't have in mind back then in the 50s the idea of machine learning. They have the idea of symbolic AI, that they will try to describe with much precision what is the task, how to solve it, and the machine will be made so that it will try to simulate the human behavior based on these rules. Another important thing is the next sentence. So an attempt will be made to find how to make machines use language. It's very important that even back then, 1956, language is considered one of the key factors, the key ingredients for artificial intelligence. Form abstractions and concepts, solve kinds of problems. So problem solving is considered in the core of AI back then. Now reserved for humans and improve themselves. So this last part, they improve themselves, could be considered something like an early mentioning on machine learning. But we will see later that it started actually in the 80s. Up to 1980s, most of the AI textbooks didn't even mention the learning as a concept at all. It started much later. And here you can see it's also, well, I would say quite funny. The next sentence. So we think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. So this for a summer is an infamous underestimate of how much it will take. And we will see also later on some example of how much they underestimated the difficulty of this. And here you can also see some of the aspects of automatic computers. How can a computer be programmed to use a language? Again, I mentioned in language, it was considered very important even back then. Here you can see a page from the original proposal. Neuron nets, so neural networks, even though it was nothing like it is today in the last 10 years, it existed back then, at least as a theoretical notion. And also self-improvement, I mentioned it before. So they did have in mind, or even back then, that it would be good that these systems could improve themselves. So I suggest that you read this proposal. It's not a big, but it's a historical document, and you see the names of the proposers. So the idea is that they try to define AI as the effort to automate intellectual tasks normally performed by humans. again, it's not necessarily related to learning. So if we manage to somehow make this task automate this task, this could be considered AI. Of course, this is not a technical definition, but it's more or less what they had in mind. So, as I mentioned before, machine learning is not at the beginning. They used symbolic AI. And the idea is that they had these rules that they tried to come up with these hard-coded rules and make some expert systems. So the expert systems based on symbolic AI were the dominant paradigm back in the 80s, up to 80s. And symbolic AI is good for well-defined logical problems, like, for example, playing chess. But it's not very good when we come to something more fuzzy or something more complex, like the everyday problems from real life, like image classification or speech recognition, or if we have some like natural language translation. So for these tasks, there were some limits, some very clear limits on what this symbolic AI approach could do. And this is why they started turning to machine learning and later on the last decade in deep learning mostly. Let's see in more detail this and what is machine learning actually. So the big question originated back in 1843. Could the general purpose computer originate anything? So we have here a quote from Lady Ada Lovelace from 1843. So Lady Ada was a friend, a collaborator of Charles Babbage. And Babbage was the inventor of the analytical engine that you can see here, that it's mentioned. So analytical engine is actually the first known general purpose mechanical computer. So we are back in 1840s. Of course, it's mechanical, it's not electrical, but the idea is that we had the first general purpose computer. And the question that was arisen back then is the analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. Its province is to assist us in making available what we are already acquainted with, which means that more or less, okay, it's very good, we managed to build this, but this can only do what we already know how to do, right? So it can perform maybe faster or with better precision, but doesn't originate something. So this question, this objection, Lady Lovelace's objection as it's known from back then, was very influential for the next centuries, actually. So even Alan Turing quoted this objection in one of his most influential papers back in 1950, where he introduced, among others, the notion of a Turing test. So we can see that this idea of having a computer actually originates something was something that researchers, even before the start of the field of AI as a concrete field, was in the minds of the pioneers. So let's see the main difference between classical programming and the machine learning approach. Here we have the two flows, two charts that show the main concept of both approaches. So usually we have, for classical programming, the human programmer which writes down the rules. Okay, so we have the rules in a specific language, so we have the program, the algorithm. And the algorithm is responsible to take the input data and turn it to the appropriate answers. So we feed the data, we ask a question, it makes a computation, it returns some output. This is what we already know as the classical programming. Now the approach of machine learning is different. So in machine learning, we have, first of all, we train it. We don't program it exactly. I mean, we program the general idea, but other than that, it's trained. And what we have is that we input the data and the answers that we want some algorithm to output. And the machine will try to, the computer will try to output a set of rules that transform the data to a representation that is close to the answers that we want. So the idea for these rules is to find, try to find the statistical structure within the training examples and find these rules that will transform the data to answers. For example, let's say that we have tagged pictures, which is quite common for deep learning. We have pictures of, let's say, dogs and cats, and we have the labels, the tags. This is dog, this is a cat. So the idea is that we feed both the data, the pictures, and the answers, tags, to a program, and this program tries to output the rules that will transform the picture data to the answer, to an output that will be as close as possible to the target answers. Now let's see, I mentioned the word representation. Let's see in more detail what are these rules, these learning rules and the representations of the data. So for machine learning, we need three things, three main concepts. The one is the input data points. So we need to feed the data. And the second is the expected output, as I mentioned before. So we feed the data, we feed the expected output. And the third thing we need in order to learn how to build this is a way to measure whether the algorithm is doing a good job or not, which will be later on what we will learn as a loss function. So an example of what would be these input points and these expected outputs, let's say, for example, for the speech recognition task, okay? The input data would be sound files of people speaking. So we feed this, and the expected output would be the human-generated transcripts in this task. So we feed these two and a way to measure, and we have the main recipe for machine learning. Now, I mentioned the notion before of representations, and you can see it here. So it's very important to understand why it's so important, this notion of representations. The input data that we will feed can be encoded in various ways, right? So for example, let's say we have pictures that I mentioned before. So these pictures can actually be encoded in, let's say, RGB, red, green, blue, the three color channels. Or they could be encoded in HSV. So, and let's see actually what I mentioned right now, why it's important to have these meaningful transformations of data. So the usual representations to get closer to the expected output. So in the example of the pictures, we have the RGB encoding, we have the HSV, the hue saturation value. So these are two encodings of the same image. Depending on the task that we want to perform, there are representations that are more useful or less useful, okay? So for example, if our task is to get all the red pixels of an image, then we can understand that the representation, the encoding of RGB is much more helpful. We just get the red channel, we have a threshold, we binarize, up, we have the red pixels. If we had HSV, it wouldn't be that easy to come up with a rule, right? Now, on the other hand, if we have as a task to make the specific image less saturated, then we can imagine just by the name that HSV, the hue saturation value, is a more helpful representation of the data. So the main idea is how to find useful representations of the data, or make this representation, find the transformations from the original data to a new representation, so that the new representation is much more helpful for the task at hand. And again, this representation vary upon the task we have, as I explained before, with the red pixels or the less saturated image. Now, let's see a dummy example of how this representation works. So here is our task. We have points on a 2D plane. So X and Y coordinates, this will be our inputs. And then we have the color. So the task is to classify each point based on the X and Y coordinate to one of two colors, either black points or white points. So pretty straightforward. You take the two numbers, you output one label. Now, as it is right now, it's not very clear what would be the rule, right? So you cannot say if X is around here, it will be white, because you can see there are blacks. Or if Y is at this range here, it will be white because, again, you have black here, right? So you want to find another representation. And here is the idea. So we have the raw data and we make a transformation. So we find a better representation, like, for example, the new coordinate system like this. And if we use the new coordinate system for the same points, we get this new, better representation. So what we have is the original raw data, and then we have a transformation based on this rule that outputs a new representation of the data. And you can see that this representation is much more helpful for the task that we have. And you can see that if it's greater than 0, it will be black for X. If it's for the new X, if it's less than 0, the new X will be white. So this is the main idea of how getting another representation of the data can be helpful, much more helpful for a specific task. For another example, you can think of the handwritten digits. So let's say we have pictures of digits that we have written by hand, and we try to classify them as if it's 0, 1, 2, 4, 9, whatever. So in this representation, the original representation, the raw data is just the values of the pictures, right? But what we want is some rules that output some new representations that will try us to identify which number it is. For example, a rule would be to try to find the number of closed loops. If there are 2 closed loops, then we have probably 8. If we don't have any closed loops, it could be 1, it could be I don't know, 3, something like this. Or we can take the horizontal and the vertical pixel histograms. So if we have more intensity in this area, it could be, for example, 7 or something like this. But coming up with these rules, it's quite difficult. So you have to think about these rules, you have to manually hard-code them, and you have to maintain them. So even if you come with a set of rules that given the picture of a digit written by hand, it can more or less predict. It doesn't mean that it will always be able to predict. You can have different resolution, you can have different colors instead of grayscale images. So it's not only difficult to come up with these rules, but it's difficult to maintain this system. And the main idea is why not to automate this process of finding these rules. So instead of thinking, okay, we have digits, we want the closed loops, we want these histograms, why not make a system, develop a system that will try to come up with this kind of rules? And this is the main idea of machine learning. So in machine learning, we search through a predefined set of operations, which is called the hypothesis space, to find this kind of transformation. So in the case of the 2D coordinate system that I mentioned before, like in this example, the idea, the space of all possible coordinate changes would be our hypothesis space. So if we have rotation of the coordinate space, this is in our hypothesis space that we search for. If we have translation of the center, this is in the hypothesis space. So inside the hypothesis space that we search for these transformations is something that comes closer to the representation we need for the specific task. Let's see in more detail how it works and how deep learning comes to this notion of machine learning, of automating this search for this kind of transformations of the data. So deep learning. In deep learning, we have what we mentioned before. So this idea of transforming the data from one kind of representation to another kind of representation. But in this case, we have this successively. So we have successive layers of increasingly meaningful representations. And this is a notion of hierarchical representation learning. So the network, in this case, I mean, we will see an example of what I mean. So the idea is that we have deep networks that are multi-stage information distillation process. And here is the example. So in this example, we have the digits that I mentioned before, and we have 4 layers. For the moment, don't care about what are these layers. They are something that we will see later on, but the idea is that they take something as input and they output something new, which is a new representation of the input data. So what we want to do is to take this input, this original input, make some transformations to this data, and the output representation to be something that will help us classify it as 0, 1, 2, 3, 4, up to 9, right? So again, we have the input information. We have some representations that come from these layers sequentially, and then we have the final output representation that will be something like this, that will be 4, for example, something. And here we can see what it would look like inside these layers. So the network transforms this digit image into representations that have two qualities. First of all, they are increasingly different from the original image. So you can see here that the representations that come out of the first layer somehow, they look like, I mean, they have things that are similar to the original input. But as we move to the next layer and to the next layer, you see that they look increasingly different than the original input. So this is one characteristic. The second characteristic is that they are increasingly informative about the final result. So here you see that we have these lines. This is not very informative of what digit it is, right? But the final representations that have nothing to do, they don't look nothing like the original, are much more informative. So these 4 representations include the information needed for the last layer to output high intensity in the 4th place, for example, 5th. So this is the main idea, that we have sequential transformations of the data so that we get new representations that distill this information, that keep the information needed for the specific task. So the next question is, how do we manage to do it? I mean, how do we get from the original input to a new representation that is better? So let's go to understanding how deep learning works in 3 figures. Before I mentioned the layers, so what are these layers is actually parametric transformations. I mentioned an example of transformation previously when, for example, with the coordinate system change, okay? So a transformation would be to rotate the coordinate system. So rotation is some kind of transformation, but it's parameterized. We can say rotated by that many degrees. So this number, how many degrees, is a parameter of the transformation. What we try to do is to find these parameters for these layers, which are parameterized transformation. Another transformation, for example, for the coordinate system would be how much we will translate the new center. So we have a center and we have a new center, right? So a parameter would be how much in X and how much in Y we will translate this center. And the idea of learning of the approach of how to do this is finding a set of parameters or weights, which is actually just numbers, like how many degrees, for the network to map the inputs to the associated targets. Now let's see the 3 images, the 3 figures that I mentioned before, and try to understand what all this means, okay? So we have the input. The input can be anything, can be the coordinates of a point, can be the pixels of an image, can be the wave or the time series of some data. And then we have the layers. So these layers are transforming the input data to some new representations. And we have another layer, we can have many layers, and in the end, we have the prediction. So the idea, the goal is to find the right values for the parameters of each function. So imagine the layer as a function, okay? The function takes something as input. Let's say a function of y is something x. So x is the input. And this something is a family of functions that could be parameterized. These parameters, the numbers that we will put in these parameters, is what we are searching for. So we have fixed transformations, fixed families of transformations, and what we try to do is to parameterize these transformations in order to get better and better and better and more meaningful representations of the data. But how can we find these weights, these numbers, and these parameters? We have this prediction Y. What we need is actually a way to see, okay, we somehow transformed the data, we rotated the coordinate system or whatever. Is this something meaningful? Is this something that the output looks something like what we actually want? Because there are many, many different transformations that we can apply to the same data. Some of them are better, some of them are worse. What we try to find is something that is better in the meaning of producing some output that is close to the output we are looking for. And here comes the true targets. So the true targets is the answer to each question. So we feed the data, we get something as output, and we have the target output. So now the question is the model did output close to the target or not? We have to quantify if it's good or not, because if it's bad, we have to make it better. If it's good, we're more or less there. And here comes the notion of the loss function. So loss function is just a function that takes as input these predictions of the model, these outputs of the model, and the targets. So the true targets, the annotations. And outputs a single number. So this number, the loss score or loss, is more or less how good or bad are these representations. So we made various transformations to the input data, we got something as an output, and this number shows this output is not quite good, or it's quite good actually. So what we try to do is to change these parameters of these families of transformations so that the output here will be as low as possible. We want as low loss score, which would mean that given the specific loss function, these predictions are very, very close to the targets, which means that this set of rules actually are able to transform the input data, let's say the picture, to the tag that we want, to whatever we want. Now, the only thing we can do after we define these families of transformations is change these weights. But the question is how to change these weights. I mean, we could change it randomly. We could say, okay, increase this, decrease this, and see if it's better or worse, which could actually work in a very simplistic example. The problem is that these weights is actually many numbers. It's some millions, usually numbers, or even more, which means that we cannot just tweak these numbers and see, it got better. It doesn't work. We have tried it. So we have to find another way, given the loss score, to change the weight so that it actually gets better and not gets just different. And here comes the notion of optimizer. So the optimizer is a very, very, very powerful tool that made all this possible, the deep learning part. We will see in more detail in the next chapter what exactly it does with the backpropagation, but the main idea is that given the specific model and given a specific input to the model and the specific targets of what we want the output to look like and the loss function, it will take the result of the loss, which again shows if it's good or bad, this representation, and we'll try to make small updates to these weights in order to make the model better. And there is actually a way to do this. So this idea of optimizer, we have tools that make small changes to this weight so that the next output will be a bit better than the previous, theoretically. Now, we saw more or less the theoretical idea of how machine learning, specifically deep learning, works. So we have the input, we have various layers of transformations, and we have the output, and we want the output to be more or less similar with the target. Now let's see what we have already achieved given this set of tools that we will see in more detail later on in the next chapters. So here are a few things that we have achieved just by using this technique. Near human level image classification. We are actually pretty much there, and I think that right now it's better than single human, the image classification. General image classification. Here, for example, if you have something more specific like medical images, X-rays, it's not always there yet, but in many cases, specifically for general image, it's close to human or even better than human. Near human level speech transcription. So if you don't have a very heavy accent like mine and you more or less can understand someone speaking, then the machine can also more or less understand speaking and it can get the transcript. Another one is near human level handwriting transcription. Again, if you have not very bad handwriting, I mean, your handwriting is not very bad, then the computer is actually, there are algorithms that are actually able to transcribe this, to get the text. Dramatically improve the machine translation. Not there yet for actual, for human level machine translation, especially for some pairs of languages, but it's way better than it was, I don't know, 5 or 10 years ago, machine translation. Another thing is dramatically improved the text-to-speech conversion, so more natural speech from bots right now. Digital assistants like Google Assistants or Alexa or Siri, they are getting better. Again, not there yet, but they're getting better. Near human level autonomous driving, we are quite good in autonomous driving even now, in comparison to the human driver. And other things like improved ad targeting, improved search results on the web, ability to answer natural language questions. Again, not there yet, but there are some pretty impressive results the last couple of years. Superhuman Go playing. This is actually something that we consider difficult. I know that now it might seem like, yeah, it's another game that we managed to solve. It was one of the tasks that we would consider it will take more than 30 years to even get close because it's so much different than chess. Indeed was, but we got it. So although deep learning is fairly old, to conclude this, it's an old subfield of machine learning. In the next, from 2010s that it became very popular, we have achieved all these results. It's pretty impressive. And this has been achieved by the general theoretical idea that I presented to you before, and we will see in more details in the next chapters. So we have produced remarkable results on things that were considered natural for humans, but elusive for machines. The problem is that, okay, we have achieved this, but don't believe the short-term hype. What does this mean? So the idea is that we still have a long way to go for some things that some people or institutes or companies present that, okay, we are almost there. We don't have believable dialogue systems. So they are impressive in comparison to what we had before, but they are not there yet. We don't have human level machine translation across arbitrary languages, especially if we go to something more linguistic, more like poetry, it's very bad. We don't have human level natural language understanding. We have good level, but not human level at any case, and many more things. And it's actually mentioned in the book, this sentence, that talk of human level general intelligence shouldn't be taken too seriously. It could be considered controversial because some people say we should take it more seriously. But the reason it's mentioned is the sentence behind that. The risk of high expectations for short term is that as technology fails to deliver, the research investment will dry up, slowing the progress for a long time. And it has actually happened. So high expectations that fail to materialize cause problems because the society expects something we say it's almost there, we don't deliver, and then they say, okay, it's a lost cause. And as I mentioned here, it has happened. So Minsky, one of the founders, if you remember the name from the proposal that I showed to you before from 1956. So this guy, 1965, said that within a generation, the problem of creating artificial intelligence will substantially be solved. It didn't. And 3 years later, from 3 to 8 years, we will have a machine with the general intelligence of an average human being. Again, it didn't. And the problem is that things like this cause these problems that researchers and governments found turned away from the field when they saw that we are not actually there and there is no light in the end of the tunnel. And this marked the start of the first AI winter. So there was a big hype. Researchers were on symbolic AI. We were almost there. We were not there eventually, and it froze for many years. And it happened again, second AI winter, and it will probably happen again. I mean, we will not probably manage to deliver all this short term. So again, at least according to the author, it's important to know where we are, what we can achieve, what is way further from achieving, which is not, of course, clear again for Go. Even 2 or 3 years, 1 year before achieving to solve the goal, to have superhuman level at Go, we consider that it's impossible. So it's not very clear what is impossible. Maybe one of these things we will solve it in the next 5 years, but it's highly improbable. Let's continue. So we saw what we have achieved. We saw why we shouldn't believe everything we hear about what we will achieve. Let's see a brief history of what was before deep learning in machine learning. So deep learning is just quite recent. Well, it existed slightly before, but it's recently the last 10 years that we have the good results. But there were good results actually before. So the last two slides I want to show, one of them is the brief history, and it's this one. Now, if you have the book, it's way more detailed. Here I just mentioned them because of time limits. But it's quite interesting to read in the book and also in other books the history of machine learning. Actually, it's not just history, because many of these approaches are slightly different. They use them nowadays, and for some kind of data, these actually work better than deep learning. So deep learning is very good for specific type of data, like for language or for, I don't know, the image, computer vision. It's not for everything. For example, they used back then probabilistic modeling, so naive-based classifiers. As it's mentioned in the name, they were pretty naive in the concept, but pretty strong. I mean, they had powerful, and they were quite powerful. The results in specific tasks were very good, and the good thing, it was quite easy to train them. It didn't need what we need right now with deep learning. Another thing is the early neural networks. You can see a description of what exists before in the book, like the perceptron or even convolution layers that we will see in 4 chapters, I think. So things existed back then. It's just that other things were missing in order to get to where we are right now. Theoretically, convolution networks existed back then, for example. Kernel methods, SVM, very, very powerful method. So you can see here very fast what was the idea. The idea is that if you remember what I mentioned again and again about the representations and the transformation of the data, the whole idea with the kernel methods is that you take the input and you project them in a higher dimensional space with specific features, and in this space it's easier to distinguish. So you can just have a hyperplane that distinguishes everything. And if you project it back to the original space, like for example here in the 2D space, you can see a border between among the positive and negative, or the white and black. So the idea of this is, again, find another representation of the data, make this transformation to another space, then find the border, and then take it back to the original representation of the data, and you have the border there. So very powerful. It's used even now with some modifications, and was actually the way of finding these kernels, these transformations, these new representations was handwritten. So they had to actually come with new kernels, and I got this kernel has these results. It's quite interesting how it worked back then. It was not automated. Another thing, the last one that I will mention is decision trees. So again, very powerful for specific tasks, very good, very easy to train. If you have many decision trees, so decision trees is just the notion of, okay, we have this value, is it, let's say, greater or less than this threshold? It's less. Okay, go to the next one. It's this feature is greater or less than this, it's less. Let's go here. So it's this kind of binary trees usually. And you have also, if you have many of them, you can have random forests. And these things, again, were very good in specific tasks. And this is why we had these expert systems that were very, very good even back then, even in the 80s, for example. The problem with all these methods is that they are shallow. So shallow learning, as it's written here, which means that they had one layer of new representation. We have the input data, and we have one chance to transform to something meaningful. Which means that if it's not easy to make this transformation, we have to feature engineer the input so that it's closer to what we are looking for, and then have this automatic transformation, this learning method to learn the final transformation. The difference now with deep learning is that we have incremental, layer by layer way in which increasingly complex representations are developed. What this means, and the second sentence, that these intermediate incremental representations are learned jointly. So here, from all these words, the jointly, I think, is the most important, because you could say, okay, we have decision trees. They can learn to make a new representation, right? So why not stack decision trees? We have the raw input, the raw data, and we pass them through a decision tree. We get a new representation, which is better. And then we feed this to a new decision tree. We get another representation, even better, until we get to the final representation, which is close to the target. The problem is that we couldn't do this because we cannot learn them jointly. So the big difference with deep learning is that we have this layer by layer way of increasingly complex representation that are developed jointly. And this is the huge difference with all the previous methods, that the whole network learns the representation all together. We don't have one layer, we learn what we want to learn, then we go to the next layer, etc. So this is why deep learning is important, but let's see why the last slide, why it happened now, because what was missing before and we couldn't do this, right? So you probably know some of this, but let's mention it's not only this, okay? There are more things that were important, but these are some of the important things that were missing before. So why now? Now we have better hardware. So better hardware, specifically GPU cards. These systems in deep learning, especially the big networks, require many millions of parameters to be tweaked, millions of billions of operations, of flops, which means that we didn't literally have the way to do it before. We didn't have the hardware to run these computations before. Nowadays, the last 10 years, we have the systems that we managed to use the system that existed and develop new systems that are more powerful for this specific thing. Another thing is the data set. So data is very important for deep learning. You have probably heard that deep learning needs big data, although it's not always the case. It's very usual the case. And what made possible to see that deep learning actually works is that we had these data sets and these benchmarks like ImageNet, which included 1.4 million images, which they had annotated all of them in 1,000 categories. It was a big thing just to think, okay, let's take 1 million plus images and have them annotated. I mean, things like this made it possible, even if they couldn't see back then, not very back, it's quite recent, that this will have some kind of good results, whatsoever beautiful, I mean, incredible results. And another thing is the algorithm advances. So we had, as I mentioned before, this the theoretical concepts of neural network, of layers, of perceptron, even convolution layers, but it had some limits, and we had to figure out new things, like we will see ResNet, to make it possible to train even deeper networks that didn't exist before. It was just the last years that it was developed, or BERT for language. Some other things that are also important is the democratization of deep learning. It's not in every field that you can see this, that, for example, back then, in order to deal with machine learning, you needed significant expertise in C++ or CUDA for something like deep learning, which only a few people possessed, even 10 years ago. Nowadays, if you have the basic knowledge on Python scripting, it's enough. You can write a very good classifier for images. You can write, I don't know, some another task. It's very, very easy nowadays to do this because we have the tools. And the good thing is that these tools are open source. Again, it's not very common in other fields to have these open source libraries and tools that you can use. So we have TensorFlow, we have Keras, PyTorch, NumPy for computations, we have OpenCV for images, NLTK, we have Hugging Face. All these things are help the society to, and the community of the deep learning to develop new and build on this and develop new and build on this. And this is one of the reasons we are here right now. So with this slide, I wanted to close the presentation. And we can move to the Q&A. I think we have some minutes. So thank you very much. This was the end of the presentation of the first chapter.